Hello and welcome, class, to the conclusion of Chapter 13, wherein we are going to be talking about unique solution properties, and these types of properties are known as colligative properties. But we can think of these really as solution properties with just, a fancy word for solution instead. Alright, so what types of properties are we going to be talking about that are unique to solutions? Colligative properties are known as the physical properties of solution that depend on concentration of the solute particles dissolved. So the types of properties unique to solutions that we will be talking about are those that the solute particle present is able to impact. The four ones that we will be introducing are known as boiling point elevation, freezing point depression, vapor pressure depression, as well as the introduction of osmotic pressure. So the fact that the boiling point increases in the presence of solute, as well as the freezing point will decrease, the vapor pressure decreases, and the fact that osmotic pressure exists, all depend on the concentration of solute particles. How much solute you have will directly impact how extreme these properties manifest. So we'll be introducing what each of these properties look like, how they're defined, how we measure them, etc. But before getting there, we're going to have to talk about the amount of solute that we have in solution. Now, in the previous lecture, in part 2, we introduced a new unit known as molality. And this is important, but it's not the only factor that impacts the concentration of solute in solution. As it turns out, the identity of the solute is also going to make a big difference. So we know already that molecules versus ions break down in solution differently. A scientist by the name of Van 't Hoff was studying this phenomenon as well, and now we name this particular factor known as the Van 't Hoff factor after him. What the Van 't Hoff factor is an approximation of the numbers of moles of particles that a substance will break into in solution according to its balanced equation, aka stoichiometry. Now, below, we can see two different chemical equations. The first corresponds to the molecule of sugar, and the second corresponds to the ionic compound of magnesium chloride. Now, in the first case, we can see that in the chemical equation, we are told that the molecule of sugar in the solid state will transform in the presence of water into sugar, C6H12O6, in the aqueous state. However, there are no ions that form, nothing breaks apart. Rather, the molecule does not break apart. In solution, how things like sugar, molecules like sugar, dissolve is that one molecule will separate itself from another molecule because the water is breaking the intermolecular forces between the two. However, the molecule itself stays intact in both cases, where these little rectangles I've drawn represent the molecule. So as one molecule of sugar breaks itself apart from another molecule of sugar, ultimately the numbers of particles that we have in solution will equal those that we started with. How we represent this is with a Van 't Hoff factor being equal to 1. One molecule of sugar dissolved to create one molecule of sugar. If we have a lump of sugar that's comprised, let's say, of 1 trillion molecules of sugar, it will dissolve, but it will still create 1 trillion molecules of sugar, just in solution instead of in solid state. Because the ratio there is 1 to 1, the Van 't Hoff factor is 1 as well. So when it comes to molecules, things that do not break into smaller pieces, things that don't break down into ions or smaller atoms, the Van 't Hoff factor will always be 1. Ionic things behave differently. As we know, ions break down in solution into charged pieces. So magnesium chloride, for instance, breaks down into 1 magnesium 2+ ion and 2 chloride ions. We can see the magnesium chloride is labeled as a solid on the left. The magnesium and the chloride are labeled as aqueous on the right. They have dissolved in the presence of water. They have, as we can see in the chemical equation though, gone from 1 piece to a total of 1 plus 2 is equal to 3 pieces, right? 1 magnesium ion plus 2 chloride ions equals a total of 3 pieces that have broken apart in solution as the result of the magnesium chloride dissolving. This is the impact of the Van't Hoff factor. If you are working with something that is ionic as opposed to molecular, the concentration of particles in solution is going to be higher than what you would expect based just off of the concentration of the reactant, because after everything breaks down in solution, you're going to end up with more particles than what you may necessarily have been expecting. So the Van't Hoff factor is our way of taking this into account. If you are working with an ionic substance or anything that breaks down into smaller pieces via chemical reaction like so, we are going to have to take that into account in our subsequent property equations, which we are going to introduce now. The first of our colligative properties to discuss is known as boiling point elevation. The boiling point elevation is an observation that the boiling point of a solution is higher than that of its neutral solvent. This is caused by an increase in the intermolecular forces present inside of the solution. An increase in intermolecular forces increases the energy that must be gained in order to transform the liquid solvent into a gas. All right, so again, the boiling point of solution is higher than that of solvent. Hence why we call this boiling point elevation, because the solution's boiling point is higher than that of just pure solvent. All right, so if we think of just a pure solvent, we know that we have to put some type of energy in to get a particle of the liquid to boil out, to break that surface tension, to break the intermolecular forces with the surrounding waters, to turn it into a gas. This becomes even more tricky, however, when solute particles are present, and I'll color solute particles as just like red dots instead of the hollow dots. Well, each one of these red dots is going to be surrounded by a particular number of solvent particles in the spheres of hydration arrangement that we've talked about already. So the solvents will not only be bonded to each other, but they need to be coordinated around a solute in order to stabilize the solute in solution as well. So we're going to have these intricate patterns of solvent particles almost trapped in position because if too many of them leave, the solute becomes unstable. So now they're not only bonded to each other, but bonded to a solute, and the solute's presence matters here. We're going to have to put in even more energy than what we previously expected to be able to overcome this energy requirement and kick the solvent out of solution. So how we can calculate and or predict what the boiling point elevation of a particular solution is going to be is with the equations here on the left-hand side. The delta TB on the left-hand side stands for or represents the boiling point elevation itself by how much has your boiling point changed. We can find the boiling point elevation by taking the Van't Hoff factor, which is represented by our variable I, multiplying it by the constant of boiling that pertains to your particular solvent. So there is a table of these constants that can be found towards the end of chapter 13 in our textbook for a given number of solvents again. So feel free to check out that table in the book if you need a particular capital K sub B. It is just a constant value and it will depend on the solvent itself. All right, and then we can see this little lowercase m here. This m does not stand for mass, rather it stands for molality. So that new concentration unit that we introduced in the previous lecture that has, again, temperature independence is going to be very useful here because we're working really close to the boiling point of a liquid. So the phenomenon is temperature dependent, meaning that we're going to need a measurement of concentration that is temperature independent. All right, so once we know the boiling point elevation itself, we can insert it into the equation down below here, where T sub B naught is the standard boiling point of the solvent. So for instance, the standard boiling point of water is 100 degrees Celsius. If we can find the boiling point elevation dependent on the presence of the solute, well then we can add the two together to find the new boiling point of the solution. So let's look at how we use this type of calculation to find something new about a solution versus the pure solvent. I love this example problem. The reason why is I grew up in a household that assumed that if you add a little bit of salt to your water that is boiling, like if you're making pasta or, something even simple as mac and cheese, that addition of salt is going to help cook the food faster because you're changing the boiling point of the solution, right? You're changing the boiling point of the water so the noodles cook faster. It wasn't until I got to college, though, and I ran this calculation for myself that I learned that that is an exaggeration to the extreme degree, and all that salt is doing is just flavoring your water to flavor your noodles. By calculating what mass of salt, or sodium chloride, must be added to approximately 6 quarts of water, so this is just a standard pot of water, 5.68 kilograms total in mass, in order to increase the boiling point of that water by even 1 degree Celsius. Now we can see that we're given the standard boiling point constant for water, which is 0.52 degrees Celsius per molality. So this is our unit exchange here. This is temperature per molality or concentration unit. All right, you have the equations though. The problem itself is not too tricky so long as you're keeping track of what values go where. So I'm gonna let you guys try this problem out for yourself before I interject. All right, so hopefully you paused the video and took the time to digest what we have talked about and see if you can't make sense of the equations for yourself. Where the primary equations that we are going to be needing are delta T sub B is equal to I kBm, as well as our molality equation, where molality is going to be equal to moles of solvent, which is sodium chloride, all divided by kilograms of the solvent, which is going to be our water. Ultimately, we are looking for mass of sodium chloride, or mass of solute, in this problem. We are told a variety of information here. So let's just start kind of partnering up what we know with the equations that we're going to be working with. First and foremost, we can see that we are given a mass in kilograms of water, which is our solvent. So we can insert our mass of solvent in kilograms into our molality equation below, 5.68 kilograms. We are also told what the boiling point elevation is. We are increasing the boiling point by 1 degree Celsius, which means we are going to be elevating it by 1 degree Celsius, so this is equal to our TB. We are also, last but not least, told what our KB is. We're going to plug that into the right-hand side of our equation right here. All right, so it looks like the pieces of information that we are missing or do not have are molality, moles of sodium chloride, as well as it doesn't appear as though we have a Van 't Hoff factor immediately present. So there's a lot that we still have left to find before ultimately we can solve for mass. And so if we're kind of trailing this problem from the end back to the front so we can kind of figure out in what direction we should even go, like what are we solving for here, how do we start, is to find mass of sodium chloride, Even though mass is not explicitly present in any of these problems for sodium chloride, moles of sodium chloride is. And as we've seen so many times in the last couple of chapters, if you need a mass and an equation is useful that contains moles, find the moles, use molar mass to convert between the two. So ultimately, using the equations at hand, we need to find moles of sodium chloride. And the molality is going to be the linker between these two equations. Well, since our first equation, the delta T sub B is equal to I K B M, seems to have a little bit more going for it at this moment, since we have 1 degree Celsius, we already know what our constant value is, the 0.52 degrees Celsius per molality. M is an unknown. It seems like the only piece of information we really don't have yet to fill in and solve for molality is the Van 't Hoff factor. Well, we just saw a couple of slides ago, how to find the Van 't Hoff factor is by observing how the solute actually breaks down in solution. What our sodium chloride does in solution, as we have seen many, many times before, is break into sodium plus and chloride minus. So to determine the Van 't Hoff factor, what we need to look at is what's the sum of the product particles here. Well, it appears as though we have 1 sodium and 1 chloride, meaning that our Van 't Hoff factor is going to be 1 plus 1, or 2. So even though the Van 't Hoff factor was not explicitly given to us in the problem, we were told what the identity of the solute was, meaning that we could use the identity of the solute to find the Van 't Hoff factor. This is going to be true for every future problem. If you are told the identity of your solute, you are able to find your Van 't Hoff factor. All right, well now we can see we have 1 equation and 1 unknown, so we can rearrange and use our boiling point elevation to solve for the molality of our problem, or the molality of our solution. Molality. I'm just gonna write that out explicitly since we have molalities and masses running all over the place. All right, so our molality, when rearranging and solving for it, is equal to 0.962 little m. Now this molality we can plug directly into the equation that we've already set up, where molality is equal to moles of sodium chloride divided by 5.68 kilograms. In other words, the moles of NaCl is going to be equal to our molality times our mass of solvent, also known as 0.962 molality, or moles divided by kilograms, multiplied by 5.68 kilograms. Kilograms will cancel out, giving us a total calculation of moles being equal to 5.46 moles of sodium chloride. This is awesome to find now that we know how many moles of sodium chloride we are working with, like how many moles of sodium chloride are necessary to raise the boiling point of water by even 1 degree Celsius. We can use this to calculate the mass of sodium chloride. Right, so in order to convert from moles into mass, we're going to need the molar mass of our sodium chloride, which, again, all we need to do is look at the periodic table to find that there are 58.44 grams of sodium chloride per every 1 mole. Crunch, crunch. And we find that we need 319.2 grams of salt in order to raise the boiling point of water by even 1 degree Celsius. And if you doubt how much salt this is, just to give you a visual, this is just over 1 cup of salt. So if you, like me, ever grew up, or did grow up, learning or being told that adding a pinch of salt is going to help the noodles to cook faster, that's not true. You'd have to add a cup of salt to make any type of significant difference to the boiling point of your water. All the salt is doing is flavoring the noodles, which is good, but it's not helping them to cook any faster. Well, since we have discussed boiling point elevation, it's time to turn our attention to the other end of the temperature spectrum. Let's talk about freezing point depression. So as it turns out, the freezing point of a solution, is lower than that of the pure solvent. Hence why we call this a freezing point depression. Depression meaning that we are going down. The reason why there is a freezing point depression is because solvent molecules must separate themselves from the solute in order to solidify, in much the same way that the solvent molecules needed to pull themselves apart from the solute in order to boil. We're going to have to really pull the energy out of the system in order to coax the solvent away from the solute and force it to solidify. Now, freezing point depression is something that we practically take advantage of, especially where I live here in Michigan, pretty regularly in the wintertime to help salt the roads. So that's exactly what we can see in the picture that is provided here, is that this is a salt truck just running through town, depositing salt, as we can see a bunch of like snow here on the ground, to try and melt the ice and melt the snow on the roads to make it safer to drive. How this works requires that the salt dissolve in water, right? It needs to dissolve into the solvent to make a solution for the boiling point to depress in the first place. So what's pretty cool is that as the truck drives down the road, the pressure of the tires on the road itself, like on the ice and snow, is going to cause the ice and snow for a fraction of a moment to like melt. In addition, if it's a sunny day, the sun is going to help provide enough thermal energy for this top layer of ice to thaw into a liquid. There's always going to be a little bit of liquid present, even if we are not able to perceive it. This is what the salt that we throw on the roads is able to dissolve in. So as the salt dissolves into this layer of water, what it's doing is preventing it from refreezing. So as it's preventing this water from refreezing, the water is going to maintain thermal energy to remain a liquid, and this little bit of excess of thermal energy is going to seep into the ice down below, melting another little bit of a layer, helping the solute to disperse. And as more and more salt kind of makes its way into the system and more salt finds its way into new layers of liquid, we're going to see the layers of ice and snow on the surface of the road slowly dissolve away. Right, so again, there are more complicated factors than just salt on ice makes it to melt. We need to make sure that there's a little bit of liquid water present. This may occur just because of people walking around. This may occur because of the sun. But during the middle of a blizzard, we can't just throw a bunch of salt on the road and say like, it'll melt. Like, we need to make sure that the salt is on the top layer, that this top layer is going to have a little bit of liquid, and the effect of the boiling point depression is going to cascade through the layers until eventually everything is melted. So it's a pretty cool phenomenon, pun intended, and we can use the equations down below to calculate exactly what this freezing point depression is in much the same way that we're able to use the boiling point elevation equations. So I'm just going to label the variables here. We're not going to use these in a problem explicitly right now, but they function in exactly the same way as the boiling point elevation variables and equations do. So delta T sub F is the measure of our freezing point depression. So this is how much our freezing point is going to change in the solution relative to the pure solvent. I is going to be equal to, again, the Van't Hoff factor, which if you know the identity of your solute, you can determine. Here, the capital K sub F is another constant that is going to be dependent on your solvent. Dependent on solvent. And last but not least, our M here, the lowercase m, is another measure of molality. I just realized I wrote like molality. There, if you're spelling along with me, we can spell it together. Okay, so if you have your first equation down, freezing point depression being equal to a combination of our Van 't Hoff factor, this constant for the solvent, and molality, we can use this freezing point depression in combination with the freezing point of pure solvent, which is our capital T sub F with a naught, to find the freezing point of solution, or the new freezing point. So we can already CA gauge the larger the concentration, the greater your freezing point depression, the lower your new freezing point is going to be. Similarly, the more particles your solute breaks into according to the Van 't Hoff factor, the greater the freezing point depression and the lower the new freezing point's going to be. The next colligative property that we have to introduce is known as the vapor pressure depression. In much the same way that we've already seen boiling point elevation and freezing point depression, the vapor pressure of an aqueous solution is going to be less than that of the pure solvent, hence why we call this also vapor pressure depression. The vapor pressure decreases for the exact same reason that the boiling point elevates and the freezing point depresses as well. The presence of our spheres of hydration are going to keep the solvent in place. So we've already explained that the presence of a solute, which I'm also going to again here draw as like little red circles, inside of a solution is going to lock our solvent in place via these spheres of hydration. Since each of these solvent particles are occupied stabilizing these pesky little solute particles, the solvents are not going to be able to boil as easily. This we've talked about already. Well, this applies to the concept of vapor pressure as well, because if we remember, vapor pressure is the presence of the, or the pressure of the gas created by the ambient liquid just evaporating sort of naturally in equilibrium due to its kinetic energy into a gas. And the pressure of this vapor of the solvent, or with the same identity of the solvent above the liquid surface, this is our vapor pressure, right? So the pressure of these particles kind of directly above the surface. Well, if these particles are so involved with the solute, they're not going to be able to evaporate as easily, right? They're going to have to stay inside of these spheres of hydration in order to stabilize the solute. This means that not as many particles are going to be able to evaporate, which effectively lowers the naturally occurring vapor pressure. In the late 1800s, a scientist by the name of Raoult published this following law. And again, a law is a consistent set of experimental observations. The partial vapor pressure, or PVAP, of a solvent above a solution, again, we're looking at this as a colligative property, how does the solvent change as it becomes a solution, is equal to the product of the mole fraction of the solvent, which is represented by variable chi sub solvent, and the vapor pressure of the pure solvent, or PVAP naught, where the naught, again, is what is representing here the pure solvent. So the construction of the equation we can see down below corresponds to this definition. The vapor pressure of our solution is going to be equal to a fraction of the vapor pressure of the solvent, right? So that's another way to phrase Raoult's law. The vapor pressure of our solution will be a fraction of that of the pure solvent. The fraction with which it is going to be reduced by is equal to the mole fraction of the solvent, which we have talked about what a mole fraction is already. So the mole fraction of the solvent can be written, just as a reminder, this equation we haven't seen since chapter 11, so it's been a while. The mole fraction of our solvent is going to be equal to the number of moles of solvent present. So again, the notation of solvent here is going to be really important, divided by the moles of the solution, where the solution represents the total. So what the mole fraction here is looking at is proportionally the more the solvent we have inside of our solution, the closer our vapor pressure of solution will be to that of the natural totally pure solvent. However, proportionally, if there is more solute present, the ratio of solvent to solution goes down. In other words, as the moles of solution increases because we are adding more solute, however the moles of solvent don't change, our mole fraction goes down, therefore the vapor pressure of the solution will also go down. All right, so what this equation for Raoult's law assumes is that the solute itself is non-volatile and does not contribute to the vapor pressure. Here in Raoult's law, in its simplest form, we are only looking at how the addition of the solute impacts the solvent, but does not directly contribute to the vapor pressure itself. So, in much the same way that I have done previous problems, I would love for you guys to pause the video and attempt this problem down below for yourself, just to see if you can't make sense of Raoult's law and all of the corresponding variables. In the problem, we are told that we have 3.73 moles of glycerol, which is a non-volatile, yet still water-soluble liquid. It is added to 20.8 moles of water. What is the vapor pressure of water? It's still going to be the solvent, our water here. What's the vapor pressure of the solvent above the solution at the normal boiling point of water? All right, so let's come back together and solve for the vapor pressure of water above the solution, as water is still going to be our solvent here. So we are going to be using Raoult's law's equation. Vapor pressure is equal to the mole fraction of our solvent multiplied by the vapor pressure of our pure liquid. All right, and I'm going to also be explicitly clear here. The textbook uses slightly different subscripts than I do. I acknowledge that this is a point where I am varying from the labeling of the textbook, and the reason why I do it is just for clarity. I truly believe that these labels are a little bit more helpful. They're a little bit more clear. So if you do use the textbook and you're reading along, working through example problems, which I heavily encourage, just be aware that my labels are going to be a little bit different than that of the text. But we're going to move forward anyway. All right, so we need to find our vapor pressure of the solution. This is our big ol' question mark. So in order to find this, we're going to need to determine what the mole fraction of the solvent is, as well as what the vapor pressure of the pure solvent is. So let's start with our mole fraction. Now the mole fraction of the solvent is going to be equal to the moles of the solvent divided by moles of solution. We're going to take this and multiply it by the naturally occurring vapor pressure, right? Want to make sure that my equality on the left is actually equal to my equality on the right. All right, so in the wording of the problem, we can see that we are given moles of solute. We are given moles of solvent. And it looks like that's the only number, our set of numbers explicitly given to us. So we can use this or these values of the moles to actually find for our mole fraction. The moles of solvent we're going to place in the numerator up above, 20.8 moles of our water. And we're going to divide this by the moles of solution. Now here's something that we also have in common with our previous lecture. Anytime a label corresponds to the solution, this will be equal to the sums of the solute and the solvent. So even though moles of solution is not explicitly given to us, we are told what the moles of the solute and the moles of the solvent are. So we can just put both of these numbers in the denominator, because the sum of the moles of our solute, which is the 3.73, and the moles of our solvent, the 20.8, should be equal to the moles of the solution in total. So whether we explicitly solve for our mole fraction or we just leave it in parentheses like this is totally fine. If you are the type of person that kind of crunches the numbers as you go, what you would find is that the mole fraction for our solvent is equal to 0.848. And this number is unitless since the moles in the numerator and denominator will cancel out. All right, last but not least, we need to know what our vapor pressure is for our neutral water. Well, if we turn our attention to the problem, a pressure is not explicitly given to us, but it is implicitly given to us thanks to the wording of the, quote, normal boiling point of water, end quote. This tells us what the vapor pressure is that we are observing, because by definition, the normal boiling point of water occurs when the vapor pressure of the solvent is equal to 1 atmosphere, right? This is a definition that we saw back in chapter 12, and now it's coming back to give us a little bit of additional information. This 1.0 atmospheres is the vapor pressure at the normal boiling point of water. So we can just insert this 1 atmospheres down below, and we can see ultimately we're taking 0.848 and multiplying it by 1 atmosphere. This tells us that the vapor pressure of the solvent above the solution of glycerol is going to be equal to 0.848 atmospheres. Now numerically, this may not seem like a big deal, but it is actually pretty significant. So at 100 degrees, pure water is going to boil because its vapor pressure matches that of the ambient atmosphere. This solution of glycerol has a vapor pressure that is less than that of the ambient atmosphere, right? It's less than 1 atmosphere's worth of pressure, which means that this solution of glycerol is not going to be boiling, even though it's at 100 degrees Celsius. This totally matches with our previous definition of the boiling point elevation. We've added a pretty significant amount of solute into the solution, which means its boiling point will elevate to above that of 100 degrees, and its vapor pressure as a result is also not going to be at a total of 1 atmosphere yet. So both Raoult's law and the boiling point elevation, as well as we can also ascertain with the freezing point depression, they're all going to be working together here. So our answers should all be self-consistent. However, not all solutes obey the ideal form of Raoult's law. And the reason why is sometimes we mix liquids in with liquids, right? If we think of one really great example, fingernail polish remover, this is actually a solution of acetone in water, and acetone is a very volatile liquid, meaning that it also evaporates pretty easily. So if your solute is a volatile liquid, or if you have multiple solutes that happen to be volatile liquids, then the solvent and the solute are going to contribute to your total vapor pressure, which I'm still going to represent here with a P sub vap or P sub vape. So how we approach this type of problem if multiple solutes are volatile along with the solvent is we can actually just combine Dalton's law with Raoult's law, which is the equation that we can see down below. So because the particles that exist above a solution in gaseous form are gases, let's see, so here's my container, here's my liquid. It's not the best, but let's say we have mixed together 2 different liquids, one of which is going to be really abundant because it's the solvent, the other will be less abundant because it is the solute. If this solute is volatile, it will exist above the surface of the liquid, just how the solvent will. And because both of these things, once they are evaporated, are gases, just as we've seen before, we can apply any of the gas laws that we talked about in chapter 11, including Dalton's law. So Dalton's law is the first half of this equation we can see here, where the total vapor pressure is going to be equal to the sum of all of the partial vapor pressures, where let's just say A is the solvent in this case, and we'll label B as the solute. Doesn't really matter which is which since we're adding them together. If we have any additional solutes, like a second solute is mixed in or even a third, we would just keep adding on the partial pressures here, hence the ... So this would be any additional solutes. All right, well, as we've seen already though, the vapor pressure of any one of these components is equal to the mole fraction of that component times its like normal vapor pressure. So for instance, if A represents our solvent, as I have labeled here, then on the right-hand side of this equation, which is going to be the Raoult's law portion of this equation, our chi sub A is going to represent the mole fraction of solvent, and our P sub A naught is going to represent the regular vapor pressure of the solvent, right? And then chi sub B would be the mole fraction of B. The P sub B with the naught would be the regular vapor pressure of that solute in its pure liquid form. And again, if we had any additional solutes, we would just keep adding them together in sum, following Dalton's law. So if in any point we're working with a problem, for instance, a homework problem, a quiz problem, an exam problem, what have you, and the solute is labeled as a volatile liquid, we're going to have to pay attention to not only how abundant it is in terms of its mole fraction, but also we're going to have to watch out for whether or not a regular vapor pressure for that solute is also provided, and take it into account using Dalton's law in combination with Raoult's law, as we can see here. So the last of all of our colligative properties to discuss is that of osmosis. Now, osmosis is not labeled as like osmotic elevation or osmotic depression. And the reason why is osmosis exists because of the solute particles. If there is no solute, then there is no osmosis. So osmosis doesn't exist in pure solvent. What osmosis is defined as is the movement of solvent particles through a semi-permeable membrane from dilute to concentrated. So we can see in the diagram below at, let's say, time equal to 0 versus time equal to, like, let's say 1 minute. However much time has passed, the volumes of solution present change. This like dotted line in between is a representation of our semi-permeable membrane, and literally what is happening is that the solvent on the left-hand side of the semi-permeable membrane is able to see or sense a concentrated solution on the other side of the membrane. In order to make the two solutions equal in concentration, the solvent is going to move from the more dilute to the more concentrated. So in t equal to 0, we can see that the concentration on the right is greater than the concentration on the left. However, after the time appropriate has passed for the osmosis to occur, enough of the solvent has moved from the left to the right that we can actually see that the concentrations now on both sides of the semi-permeable membrane are equal. Even though the volumes have changed, the volumes changed in order to make the concentrations equal. Now, if you were reflecting as I introduced osmosis, like, well, I've never seen something like that happen before. Actually, yes, you have. If you've ever eaten a pickle before, or even seen or heard of a pickle, pickles are formed by the process of osmosis. You see, the way that we make pickles is by taking a cucumber, which we can see here on the far left, cucumber, and we place it inside of a jar of brine solution. And brine is just the fancy word for salt water. So we have a ton of solute present outside of the pickle, where the pickle, or at this point it's still a cucumber is mostly just water, right? It's like a vegetable filled with juicy water. So as the cucumber is placed inside of this brine solution and all of these particles here are present on the outside, what the water does, which is again present in abundance on the inside, is going to, I realize my sentence is formed very strangely. What the water inside of the cucumber is going to do is move out through the semi-permeable membrane of the cucumber's skin into the brine solution. Now, how we flavor pickles, like with dill or like sweet pickles, spicy pickles, all you need to do is place some kind of like abundant amount of flavoring here in the bottom of the jar, and also just through general equilibrium processes, the cucumbers will pick up on these flavorings. But the reason why the cucumber shrinks in volume is because the cucumber is losing water mass. In order for this cucumber to turn into a pickle, we place it in brine water because the brine is so much more concentrated. The concentration of solute particles outside of the pickle is much greater than that on the inside of the pickle. To accommodate for this, the water on the inside moves out in an attempt to decrease the concentration of the solute outside of the cucumber, increasing the concentration of the stuff inside of the cucumber to the point where eventually we get a pickle. The quantifiable colligative property in and around the topic of osmosis is that of osmotic pressure. Osmotic pressure is defined as the pressure that results from the flow of the solvent particles through the semi-permeable membrane. And we'll talk about the equations below, but again, where this pressure comes from is as the solvent particles are moving through this semi-permeable membrane. Before actually moving through, they are going to come into contact with the membrane as a part of this like diffusion or effusion process. This little bit of contact with the wall that each of these solvent particles is making is going to cause a pressure, in much the same way that gases cause pressure on the walls of their vessels as they come into contact with them. All right, so with that logic in mind, we turn our attention to the equations here, where the calculation for osmotic pressure is equal to P equals I mRT. This capital pi is a variable that represents the osmotic pressure. So we can think of this as just another capital P. In fact, capital pi is the Greek letter for, in English, capital P. So we're just using a different language to represent the exact same variable P. This osmotic pressure is equal to the Van't Hoff factor. So we can see the Van't Hoff factor returning here, times our concentration in molarity. So we are working in moles of solute per liters of solution when it comes to osmotic pressure. The reason why we do this is we don't normally measure osmotic pressure near things like freezing points and boiling points. We're just kind of looking at ambient temperatures, and so the temperature dependence of molarity doesn't actually matter to us that much. All right, next up we have a capital R here. As it turns out, this capital R is equal to the exact same value of our gas constant R, 0.08206 liter atmosphere per mole Kelvin. And last but not least, temperature, of which, by observing the units around, we can see have to be present in Kelvin. So the setup of this equation is really similar to that of the ideal gas law, where if we rearrange the ideal gas law just by pulling volume, our V, onto the right-hand side, we can see that we're sort of in this one-to-one correlation, where we have pressure on the left-hand side, some measure for concentration in moles per volume unit on the right-hand side, R, again, being exactly equal to the exact same gas constant R, and T for temperature. The only real difference in terms of construction for osmotic pressure is the presence of the Van't Hoff factor, which was not present in the ideal gas law. So we have one example problem left in today's lecture. This is it. All right, so our problem in front of us, we are told that 27.4 milligrams of an unknown compound are dissolved in water to make a 100 milliliter solution. However, the solution was found to not conduct electricity and had an osmotic pressure found to be equal to 9.94 torr at 23.6 degrees Celsius. What we are being asked to find with this information is the molar mass of the unknown compound? Well, this is something that we haven't really ever needed to find outside of just looking at the periodic table, but sure enough, we're not told the identity of the solute. This is an unknown. So, experimentally, we have a means to find molar masses. We just haven't really had the ability to talk about it until now because the most common ways to experimentally find molar masses, at least at the general chemistry level, are all wrapped up with the colligative properties. Alright, so I'm going to let you guys try and dissect what we have here, at the very least to start solving for some variables, things like moles, for instance. That's a big hint. If we can find moles, we can find molar mass. We're just not going to go about it in the way that we normally do. So, take that as you will, and approach this problem. Afterwards, we will come back together. Alright, hello and welcome back. Let's solve this problem and then call it a day. Alright, so we have, as we can see, an osmotic pressure. We know that this problem is going to more than likely involve our osmotic pressure equation as a result. Pi is equal to I m R T. Ultimately, we are trying to find a molar mass. So how can this equation help us to find a molar mass? Well, in order to answer that question, let's ask ourselves another one. What is molar mass? I mean, normally we just look at the periodic table and find some numbers, but what do those numbers mean? They always represent grams per mole. And I know some folks still kind of mess up those units, but the units are important because they tell us what we're working with. Molar mass is equal to a ratio of mass per mole. And this mass is oftentimes in grams. Moles obviously are in moles. So if we're looking for a molar mass, we need to be able to insert a mass into this ratio, this equation, and we need to be able to insert a number in moles. Well, as it turns out, in the wording of the problem, we are told what the mass of this unknown compound is. This is awesome. We already have half of this equation in order to find what the molar mass of our unknown compound is. All we need to do is take this amount in milligrams and convert it into grams. How we do so is by acknowledging that there are 1,000 milligrams inside of every one single gram. So here we can see we need to divide by 1,000 in order to get into the unit of the gram. So in the numerator of our equation, we will have 0.02740 grams of this unknown compound. So what we can see here is we are now currently missing a value in moles. However, we can find this by using the previously mentioned osmotic pressure equation. So let's assess the variables that we have and plug them into our equation to solve for number of moles. First and foremost, it'll probably be useful, since we want to have one equation and one unknown, to rearrange this a little bit. And what I'm going to do is explicitly write out molarity as N per V, or moles per volume. This is going to be useful for us in that we only have to solve for one unknown variable inside of this one equation. Just so long as every other variable is present, it should be a pi, rewriting the pi, every other variable is present with the correct units. All right, so the units present in the osmotic pressure equation are going to be the same units that we use in the ideal gas law equation. We need pressures in the units of atmosphere, we need volumes present in the unit of liter, we need moles in the unit of moles, and we need temperature in Kelvin. How we know this is because of our gas constant R. R, again, is equal to 0.08206 liter atmosphere per mole Kelvin. So everything else that gets plugged into this equation sure better be in liters, atmospheres, moles, and kelvins. All right, so what this tells us is that the pressure that's given to us, the temperature that's given to us, and the volume that's given to us all need to be converted in some way. So our, let's write it up here, 9.94 torr, need to be converted into atmospheres. The conversion for this is 760 torr per every 1 atmosphere. This gives us 0.0151 atmospheres of pressure. So this is a very low amount of pressure, which makes sense because osmosis tends to be a very slow process. We don't have a lot of pressure moving as we don't have a lot of pressure as the solvent moves very quickly. Instead, we have this nice slow process with an intermediate amount of pressure. Our volume, 100 milliliters, is going to be converted into liters by dividing by 1,000, 100 milliliters. There are 1,000 milliliters per every 1 liter, giving us 0.100 liters. And last but not least, our temperature, we're going to add 273.15 to it to give us a temperature in Kelvin equal to 296.75 Kelvin. So now we have a temperature that works with our gas constant, we have a pressure that works with the gas constant, and a volume that works with the gas constant. So each of these variables can be inserted into our equation to rearrange and solve for n, where again, n is ultimately what we're going to be plugging into our equation for molar mass to find the molar mass. All right, so our pressure is going to be plugged into the left, 0.0151 atmosphere, equal to, well, oh no, we have a variable that we haven't assessed yet. All right, so Van 't Hoff's factor can also be found in the wording of this problem. It's just not as straightforward maybe as what it once was, assuming that we knew the identity of the material. The piece of information here that's going to be useful to us is the fact that the solution did not conduct electricity. If we think back to previous knowledge, previous experience, things that do not conduct electricity do not break into ions. Right? Ions are necessary in solution for conductivity. So if we have no conductivity, we must not have any ions. And if we don't have ions, we have to have a molecule. And if we have a molecule, we have a Van 't Hoff factor of 1. We can assume this because our particle must be dissolving in solution, but not breaking down any further into charged pieces. So for every 1 molecule of solid, we're going to have 1 molecule dissolved in aqueous solution. All right, number of moles, our variable n is unknown. 0.100 liters gets plugged into the denominator like so. R is going to take up space, so I'm just going to write R, but sure enough, it is this value of R up here. And T for temperature is 296.75 Kelvin. So from here, we have one equation, and our one unknown is n. If we rearrange to solve for this n, we find a value of 5.38 times 10 to the negative 5th moles. So we don't have a lot of stuff in solution, and this is also backed up by the fact that we don't have a lot of osmotic pressure, right? There's not as much incentive for the solvent to move from low concentration to high concentration if the concentration difference isn't actually that great. All right, so this value of n, though, we can plug into our equation up here, 5.38 times 10 to the negative 5 moles in the denominator. So we're going to take our mass, the 0.02740 grams, divided by this number of moles that we found to find a molar mass that is equal to 509.33 grams per every single mole. All right, so this is a very large compound, more than likely something that's like a pharmaceutical, a protein of some sort, something that's very large. Just because we have a large molar mass does not mean that we are working with something that is incorrect, right? Some ions, some molecules have very large molar masses indeed, and that's perfectly okay. All right, so here we have some example problems pertaining to colligative properties qualitatively, as well as calculations of colligative properties quantitatively. So definitely feel free to take your approach at these problems to get some additional practice. Practice with every new equation. It's going to be very useful to get more practice with it, to be able to identify the red flags that pop up that give you the signal for when you need to use what variables and what equations when. So, if you have any questions on today's lecture, please do not hesitate to reach out. If you have any homework, please double check and do your homework. Practice, practice, practice. And until next time, class is dismissed.